Welcome back. In the last video, we defined the notion of fixed fields for a collection of homomorphisms from one field to another field, and we looked at various examples of these fixed fields. And I also said that the main case in which we are going to be interested in is when the target and source fields are same. So you look at homomorphisms from K to K. Today we are going to prove one very important theorem, and the next video will prove another theorem. So the next two videos are two very important theorems about fixed fields, and the entire theory that we will do after will depend on these two theorems. Okay, these are two important theorems, so please pay close attention to these. And the proofs are actually just nothing more than linear algebra. So it will be very elementary, though a little computationally it will be tricky, but it is very elementary. Nothing more than algebra, linear algebra is used. So just quickly recall, K and L are two fields, and you have a collection of homomorphisms. The fixed field Kf is defined to be all A in K such that images of A under all these homomorphisms is the same. Okay, so this is a subfield of K. So clearly, of course, F is contained in K. So now the two theorems I'm going to prove, which I said already that they are very important. In the first theorem, we are going to be in this general setup where you have two fields and homomorphisms between them. In the second theorem, we will actually do the main case that we are interested in, where K and L are same. So the theorem that I want to do now, the first theorem in this video, and it says the following. So so I'm going to basically rewrite this. Let sigma 1 through sigma n from K to L be distinct. So the important assumption is that they are distinct field homomorphisms, and let F be their fixed field. Okay, so let F be their fixed field. So now the conclusion of the theorem is then the index of K over F is at least n. Okay, very simple statement. We have n distinct homomorphisms. The degree of K over F is greater than or equal to n is the conclusion. Okay, so in general, this is what we can say. So what I want to now, before I start the proof, just a few remarks. The proof will use, very importantly, the fact that sigma n are independent. So remember, their characters from K cross to L cross. So they are characters of the multiplicative group K cross in the field L. So I should, this is the terminology. Sorry. So they are characters of K cross in L, and they are distinct, so they are independent. This is our foundational theorem that we proved a couple of videos ago. So this is what we will use. Okay, and then I will also this is the crucial ingredient in this theorem as well as in the next theorem. And the second remark is really an example. So I did this in the last video. We discussed this in more detail. So I am only going to quickly tell you what happens in this with respect to this theorem. So sigma 1 to sigma 2 from K to K, they send sigma 1, I think, fixes I. Okay, so just to be consistent with the earlier notation, sigma 1 changes I to minus I, root 2 to root 2, sigma 2 sends I to I, root 2 to minus root 2. So let me, so sigma 1 sends, and sigma 2 sends I to I, root 2 to minus root 2. Then if you think about this, the fixed field of the set 1 sigma 1 sigma 2, I claim this is a subfield and of course it contains Q. So now by the theorem that we are now going to prove, this is at least 3, right? Because there are 3 distinct homomorphisms, 1 sigma 1 sigma 2. So this is at least 3, whereas this is 4. The entire degree of K over Q is 4, and hence the fixed field of must be Q, because any sub index, if you have K to Q and you have some K prime, this is 4. So this number, whatever this is, let us say this is R, divides 4. So R divides 4 and this is at least 3, that means this better be 1. Okay. So that is the explanation. So that means if this is F in the notation of the theorem, K colon F in this case is 4, which is strictly greater than 3. So the theorem is true, but the inequality can be strict. So the inequality in the theorem can be strict. So the second theorem, which we will prove in the next video, deals with this. In a special case, you assume some things about sigma i's, namely that they form a group, then the inequality is actually inequality. Okay. So that we will do later. But for now we are only saying that K colon F is at least n. That's all. Okay. So let me now start the proof. As I said, the proof is really nothing but an exercise in linear algebra, and please slowly follow this. This is not difficult and it's very nice. It's actually a very clever proof, and it uses pretty much nothing more than linear algebra. Okay. So, and if needed, you can watch this slowly and follow the proof. So, suppose the proof goes by contradiction. So, let R be the index of K over F. Suppose R is strictly less than n. So, we are trying to show that R is at least n, right. So, this is R and R is at least n. So, suppose it is strictly less than n. Okay. So, what does this index mean? It is the dimension of the vector space K over the field F. So, we are going to choose so I am going to try to squeeze everything into this screen so that you can, we have all the data in front of us. So, I am going to write smaller letters. So, let choose a basis alpha 1 through alpha r of K as an F vector space, right. This is the meaning of the index. Dimension of the F vector space K is R. That means there is a basis consisting of R elements. Now, I am going to consider the following. So, I am going to split this into two parts. So, consider the following system of, it is a homogeneous system in fact, system of linear equations with coefficients in L. Okay, what is this system? So, I am going to represent the system as a matrix. So, I have sigma 1. So, in the first row, I am going to fix alpha 1. So, sigma 1 alpha 1, sigma 2 alpha 1, sigma n alpha 1. In the second row, I am going to fix alpha 2 and sigma i's go through from 1 to n. So, sigma 1 alpha 2, sigma 2 alpha 2, sigma n alpha 2. Okay. And in the last row, I am going to fix alpha r, sigma 1 alpha r, sigma 2 alpha r, sigma n alpha r. So, this times a column of variables. So, this is n variables, right. I want this to be the 0 vector. So, this is a homogeneous system of equations. So, if you think of this as a matrix A, A is of course, what is the size of A? A is, so there are R columns, R rows, 1, 2, 3 corresponding to alpha 1, alpha 2, alpha R. So A is an R by n columns, right? Alpha 1, alpha 2, alpha n. So R by n matrix with entries in L, of course, because sigma is, remember the hypothesis, sigma i's are functions from K to L, alpha i's are in K, so sigma of alpha i's is in L. So A is an R by n matrix with entries in L, and the system is nothing but, so the system is Ax equal to 0, right? So this is a system of the form Ax equal to 0. So how many equations are there? There are R equations, I'll write that here, R equations, n variables. Variables are x1 through xn, equations are first row here times the vector, second row times the vector, last row times the vector. So there are R equations. So now you know from your linear algebra that you learned long time ago that every time you have fewer equations than variables, there is always a non-trivial solution for this homogeneous system of equations. Since R is less than n, namely since the number of equations is less than the number of variables, this homogeneous system has a non-trivial solution. Okay, say beta 1 through beta n, this is a system of solutions in L, right? So what we have is A times beta 1 beta n equal to 0. So I am not going to write all these equations, but you can read this now equation. I mean maybe the first equation. So the first equation will be sigma 1 alpha 1 times beta 1 sigma n alpha 1 times beta n equal to 0, right? That is the, so just replace x1 by beta 1, x2 by beta, x2 by beta 2, xn by beta n. So I am only going to write the first and the last equation. Last equation will be sigma 1 alpha r beta 1 all the way up to sigma n alpha r beta n equals 0, right? So there are n equations like this. Okay, so this is just collection of elements of L now, and this is 0, and at least one beta I is non-zero. So at least that is exactly the meaning of it being a non-trivial solution. So this will be useful for us later. Okay, so now let me try to, the goal now is to play with this linear system and conclude a contradiction. So what we are going to claim, so maybe I'll squeeze the claim here. Claim is, we are going to claim that beta 1 sigma 1 alpha plus beta n sigma, so maybe I'll write one more term here, beta 2 sigma 2 alpha plus beta n sigma n alpha is 0 for all alpha in K. That's my claim. If this claim is true, so I hope you are following this. This is nothing more than just playing with linear equations. So if this claim is true, so I am going to show that beta 1 alpha, beta 1 sigma 1 alpha plus beta 2 sigma 2 alpha plus dot 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 plus beta n sigma n alpha is 0 for all alpha in K. Then the function beta 1 sigma 1 plus beta 2 sigma 2 beta n sigma n is identically 0, right? But this violates the, and remember one of the beta i's is non-zero. So at least one beta I is non-zero. So this violates the independence. As I told you, this is the crucial the property that we are going to use of sigma 1 through sigma n. right? So this violates the independence of sigma 1 through sigma n, and hence r cannot be less than n. So that is the approach we are going to take. Okay, so I hope you can follow so far. The approach is, if r is strictly less than n, we have constructed a clever linear system of equations. Using the fact that r is less than n, we are guaranteed a non-trivial solution, so that beta, one of the beta is non-zero, and then we are going to prove this claim, so that alpha, sigma 1 through sigma n are in fact dependent. They are not independent, but they cannot be dependent because they are distinct characters of a group, so they must be independent, and hence the claim is that this is a contradiction. So the goal is to prove this now. Okay, so the goal is to prove the claim, and the claim is proved by essentially using just clever linear algebra, manipulation of linear equations. So let us take an arbitrary alpha in K. So we are going to show this for any alpha in K. So the claim is that this is true for all alpha in K. So I am going to start with an arbitrary alpha in K. Alpha 1 through alpha r are a basis for K over A. So write alpha as uniquely, right? So A1 alpha 1, A2 alpha 2 plus An alpha n, where Ai's are now in F. This is the important fact. Because K is a vector space over F, it has dimension R over F, and alpha 1 through alpha r form a basis of K over F. So any element in K, any element alpha in K can be written uniquely. This expression is unique. Right, and Ai's are in F. That is the important statement, important property for us. So we are going to write this. So now, so I hope you can see this. So this is the system that I am interested in. Okay, so this is the first equation. This is the second equation, is not written, but nth equation. So you have all these things. So R equations. So we are going to first multiply. So now let me start the proof of the claim. So multiply the first equation by sigma 1 A1. Okay. So I claim that sigma 1 A1 is a scalar. So if I multiply this equation here by any scalar, the equation will remain true. So what we have is, so I am going to write it here. So what we get is sigma 1, so I am going to write this like this, A1, sigma 1 alpha 1, beta 1. So you can see that here, sigma 1 A1, sigma 1 alpha 1, beta 1. Let me write the second term just so that you understand what is happening. So second term will be sigma 2, it's here, sigma 2, so I am multiplying by sigma 1 A1. So sigma 1 A1 times sigma 2 alpha 1 times beta 2 plus last term will be sigma 1 A1 sigma n alpha 1 beta n is 0, right. So that is what the, after multiplying by sigma 1 A1 we get this. Now we are going to use the important fact that A1 is in F and F is the fixed field of sigma 1 through sigma 1. So what we have is sigma 1 A1 equals sigma 2 A1 equals sigma 3 A1 all the way up to sigma n A1. Now if you look at this equation here, I am going to rewrite that. So what we get, first term involves sigma 1 A1 times sigma 1 alpha 1. So I can rewrite that as sigma 1 A1 alpha 1 times beta 1, no problem. But the second one involves sigma 1 A1 times sigma 2 alpha 1. But sigma 1 A1 is same as sigma 2 A1. So you can replace this here by sigma 2 A1, right, sigma 2 A1. So once you have it sigma 2 A1, it will be sigma 2 A1 times sigma 2 alpha 1, but that means I can write this as sigma 2 A1 alpha 1, right. So and then beta 2, and the last term sigma 1 A1 is equal to sigma n A1. So that is just sigma n A1. So sigma n A1 is equal to sigma 1 A1. So sigma n A1 times sigma n alpha 1 will be sigma n A1 alpha 1 and beta n equal to 0. Okay. So that means the first equation, so this becomes this, right. So there is, using the fact that A1 is in the fixed field, that is very crucial. Otherwise you cannot replace the sigma 1 A1 by sigma 2 A1 and then you cannot combine A1 and alpha 1 like this. Okay. So it's important to know that A1 is in the fixed field. Now you multiply the second equation by so I want to write the second equation here. So multiply the second equation by sigma 1 A2. So multiply. Okay, so I want to have all of them together. So I'll write it here and write what I get here. So multiply the second equation by sigma 1 A2. So use the fact that use sigma 1 A2 equals sigma 2 A2 equals all the way up to sigma n A2. So I get a priori sigma 1 A2. So the second equation is this. I haven't written the second equation, but it is sigma 1 alpha 2 times beta 1, sigma 2 alpha 2 times beta 2 plus sigma n alpha 2 times beta n is 0. If I multiply by sigma 1 A2, I get sigma 1, the first one will be sigma 1 A2 alpha 2 beta 1, right. The second equation using this equality will be sigma 2 A2 alpha 2 beta 2, and the last inequality, last term will be using this, it will be sigma n alpha 2 times sigma n A2. So you get sigma n A2 alpha 2 beta n is 0. Okay. So and now dot and the last point is you multiply the arc equation. Sorry, I have been writing very slowly, very small letters, and this might become messy, but I wanted you to see everything on one screen as I am doing this proof. So I hope this is better. So multiplying the arc equation by sigma 1 AR, which and use sigma 1 AR equals sigma 2 AR, which is sigma n AR. What I get is sigma 1 AR times alpha R beta 1, sigma 2 AR times alpha R, right. So originally it will be sigma 1 AR times sigma 2 alpha R, but using sigma 1 AR equals sigma 2 AR, I get this. So it's the same kind of manipulation as this, times beta 2 and all the way up to sigma n AR alpha R beta n is 0. So now this is the system that we are going to use. So this system is what is going to do the job for us. Now if you just stare at this, if you just stare at the first term in each equation, you get sigma 1 A1 alpha 1 beta 1, A2 alpha 2, AR alpha R. So if you add all of them, what do you get? So now add all the equations in star to get, so this is the last step now. We are done now almost. So if you add all the terms, all the equations in star, which is this, what is the coefficient of beta 1? So beta 1 will be sigma 1 of, sigma 1 is a homomorphism, right? So sigma 1 of A1 alpha 1 plus sigma 1 of A2 alpha 2 plus sigma 1 of AR alpha R will be sigma 1 of A1 alpha 1 plus A2 alpha 2 plus AR beta R times beta 1, and similarly sigma n of A1 alpha 1 plus AR alpha R times beta R is 0, right? So that is what we get. But this term inside the bracket, what is this? this is exactly alpha, right? So alpha is a1 alpha 1 plus a2 alpha 2 plus an alpha n. So I made a mistake here. So of course this is not an alpha n, right? So this is ar alpha r, because alpha 1 through alpha r are the basis elements, so it only goes up to ar alpha r. So this term is just alpha, right? So that is alpha, and this is alpha. So that means what we get is sigma 1 alpha beta 1, sigma 2 alpha beta 2, sigma n alpha beta r is 0. So beta n, so again I messing up the indices, so it will be beta n at the end, right? Because I have all the way up beta n's. So I hope I made no further mistakes of indices, but this is the upshot, and this is exactly what you see in the claim, right? So you get beta 1, of course I interchanged beta 1 and sigma 1 alpha, but that's okay. These are field elements in L. So this is true, and hence the claim is proved. Okay. So this completes the proof, and essentially what we have done is show that the fixed field index. So if you start with a bunch of homomorphisms and you take n distinct homomorphisms and you take their fixed field, the index of the ambient field over the fixed field is at least n. We have seen that the inequality can be strict, but it is always greater than or equal to n, and the proof is basically a linear algebra proof. I hope you understand the proof. The proof is extremely clever and uses, as you can see, nothing more than linear algebra. So I really want you to understand the proof carefully, because this is part of the beauty of the subject. So this is all what you should learn carefully. Statement is still the most important thing that we will use later, but the proof is nice. So I hope I did not go too fast or did not make it messy for you, and the proof is clear. So this is where I will stop this video, and this completes the first theorem that I wanted to prove about fixed fields, and in the next video we will do the second theorem, which restricts to the case k equal to L and shows that there is an equality in some cases. So before I stop, let me just end the theorem by defining okay, so maybe I want to use all of the next video for the proof. So let me just give you quickly the definition here. Let K over F be a field extension. This is not really a definition actually, this is a lemma. Okay, so I am going to stick to, so a field extension. Then the set of all F isomorphisms from K to K forms a group under composition. Okay, so this forms a group under composition. So the proof I will do as later, because I want to wrap up this video, and we'll come back to this later. So the set of all F isomorphisms from K to K I should write, and these are called automorphisms. If you have the same target and source, we call this an automorphism. So an isomorphism K to K is called an automorphism. That is because auto refers to the fact that it is from K to K. So the set of all F automorphisms of K forms a group under composition, and this is a very easy proof, by the way. I will do this later. Proof is very easy, because if you compose two automorphisms, you get an automorphism. Identity is an automorphism, so that's all really, there is nothing more. So the point is, this, so now this is the most important definition for us. The Galois group of the extension K over F is the group of all F automorphisms of K. Okay, so the lemma says that they form a group, and that group is called the Galois group of the extension. It is denoted by, so this is really we are getting to the beginning of Galois theory really. So this is an important object that Galois theory studies. So it's called the Galois group. Okay, so let me end the video by giving you a bunch of the examples. I will not prove many of these. I will not prove them now. They are either easy or we will come back to the proof later. So Galois group of, if you take Q adjoint I over Q, is Z mod 2Z. Okay, Galois group of Q adjoined, let's say I comma root 2 over Q is isomorphic to Z mod 2Z cross Z mod 2Z. And I'll write two more. Galois group of cube root of 2 over Q is just the trivial element. Okay, so trivial group. And finally, the Galois group of FPR over FP is isomorphic to Z mod RZ. Okay, so these are some things for you to think about this. Think about this. We will discuss more in the upcoming videos. So I wanted to define this because I want to frame the next theorem in terms of Galois group. So I defined this, but the main content of this video is this theorem that if you take a bunch of homomorphisms from K to L, the fixed field is a subfield of K, and the index of K over the fixed field is at least the number of those field homomorphisms. It's of course important to take distinct homomorphisms. Okay, let me stop the video here, and in the next video we will prove the second important theorem about fixed fields. Thank you.